on the recording, please remind me, because like sometimes I do forget to do that. I mean, I'll try to remember, but it's just not a habit to record. So yeah, thanks for reminding me. So yeah, but generally people can see what I'm writing, right? Because I mean, I'm on two devices, and on the other device I can see that it's coming up. Okay. So yeah, I mean, if you can switch on your cameras also, I mean, it will be nicer. I would say, so that I can see some faces and get some reactions. Anything. If your bandwidth allows, and like yeah, you also don't mind switching it on. Okay, good. So I guess then the question will become like, who will turn it on, and then like yeah, that person might feel like, okay, but please, if you switch on, it will be nice. It will be good for me, because otherwise I'm just teaching black boxes, and I can't like. You do ask questions sometimes, but it's better to see faces. Okay, good. So I was saying that okay, the MLFQ tries to optimize the turnaround time, and it somehow wants to run the shorter jobs first, but the OS does not know how long a job will run, so how to deal with this. And the second is going to be, it should be responsive to interactive users, right? So which is also minimizing response time. So we saw what is response time in last lecture. Okay. So today's question that we are going to address is this. How can a scheduler minimize response time and also turnaround time without having a priority knowledge about the jobs? Okay, good. All right, so let's start with some basic rules, okay? That how does this thing work? So, okay, so the first thing is that scheduler has a number of queues, as like the name suggests that it has something to do with queues. And of course, these queues are of processes or ready processes, and each queue is assigned a different priority level. uh, Different priority. So no two queues have the same priority level. And at any point, a process in ready state. So ready state we had seen in one of the earlier lectures, I think second or third, is in a single queue. And now MLFQ uses the priorities of the queues to decide which job to run. Okay. And like high priority first. And finally, if there are many jobs in the same queue, at same priority, then run them in round robin. Okay, so this is what it does. I mean, this is in a nutshell. So what it does, it maintains like different queues of priorities, and then so we'll see examples also in a short while, and then it like runs the highest priority things first, and then keeps. Okay, so in chat there are some messages. Okay, for Abdul. Cool. So yeah. So, so let's like write these down as rules. So what is going to be the first rule? And these rules will define the algorithm, the MLFQ algorithm, the scheduling algorithm. So what is rule one? Is if priority of A is greater than priority of B, then A runs, B doesn't. And rule two is going to be if priority of A is equal to priority of B, then run A and B in round robin. We have seen what round robin is in last lecture. Right? Okay, so what is this priority thing? So everything depends on that. So the question is how to assign priority. Okay, and of course this cannot be static because I mean, so this has to be dynamic. I mean, a process can, sometimes get high priority, sometimes get lower priority. We'll see how. And how does this vary? So this depends on the observed behavior. Okay. So depending on the observed behavior, the scheduler or scheduling algorithm, MLFQ, varies the priority level of the job. And generally, what is the thumb rule that if a job uses yeah, so if a job uses the CPU too much, without releasing it for other jobs, then its priority will be lowered. Okay, And similarly, if there is so these kind of jobs are like bad jobs who are like using the CPU a bit too much, then their priority will be lowered and they'll not run for at least the time being. And if a job releases the CPU frequently, then it will get high priority. Okay, good. So let's see a like very simple example. So let's first see what. So basically, okay, so MLFQ learns about the behavior of the process over time. So let's just see like a very simple thing that, okay, so how does the structure look like? So it has, suppose, I will denote the, just like in the book, the queues with higher number will denote higher priority, and the queues with lower number will denote lower priority. Okay. So now let's say this is Q4, Q3, Q2, Q1, and so generally I'll be going till Q0. So suppose Q4 has two processes, A, B at certain point, Q2 has one process C, Q0 has one process D, right? And then what will happen? A and B will run in round robin, and C and D will not run. Okay. So, I mean, this is just the basic example, but of course, this is not acceptable that C and D will never run, and we'll see because I said the priority changes. So then we'll have to see how the priority changes. Okay, good. So now the question is how to change priority. Okay. So as I said that mm, short running ones. So there are like, of course, two kinds of jobs majorly. So one is short running, as I said, and why they might be short running, because they might be interactive. They might require a lot of IO. So when they require the IO, they will release the CPU. And then there are long running, which need a lot of CPU time. But for these, actually, let's say for long running job, the response time will not be that important. Because they are not interactive, so it's okay if we can give them like sometime later, give the CPU sometime later, and then let them run for a long time. Okay. So now we'll have some more rules. So we had two rules before, which was just about priorities that if sorry, if priority of A is greater than priority of B, then A runs, B doesn't. If they are equal priority, then they run in round robin. Now we'll write another rule. So what is rule 3? It says that when a job enters the system, it is placed at highest priority. That is the topmost queue, let's say. Okay. And as I was saying that now the short running and long running jobs, so we'll have some rules for those. So call them 4A and 4B, just like the book. So if a job uses its entire time slice, so we run them in round robin, right? So there are these time slices for which each job runs. So if it uses its entire time slice while running, then we decrease its priority by 1, let's say. And rule 4B will be that, okay, if a job releases CPU before its time slice is completed, then we keep it at the same priority level. Okay, so these are the basic rules for now. So let's see some example, okay? So suppose there was just one long running job. So example 1 is one long running job. So what is this? So let's say A comes at t is equal to 0 and runs for 200 milliseconds, let's say. And suppose the time slice is 20 milliseconds, okay? Or is it 10? Maybe it's 10 in the book. So let's just be consistent and write it to be 10. Okay. So right now we are not considering many jobs. Let's see what happens when there is just one job. Okay. So what happens? So suppose we have only 3 queues for now. Q2. Why do I write it in subscript? Q2, Q1, Q0. So the job comes at, so this is t is equal to 0, let's say. Job comes here at t is equal to 0. It runs for 10. So this is 10. Runs for 10 milliseconds at the top level. Why? Because when a job enters, it starts at the top level. Okay. Now, but then it finishes its time slice at the top level. So it will be put at the bottom level, at one level below. And then it will be run because there is no other job which has higher priority than this right now. So then it will run at this level for 10 more seconds. And then finally here, again, it will be demoted, like its priority will be reduced. And finally, at this level, it will run for a long time because there are no more queues, and then it will finish. Okay. So is there any question about this, that what happens in case of one job? So we have just followed the rules.
Excuse me, sir.
Yeah.
Sir, why did we place it in Q2? Why not in Q3 or Q4 or something?
I mean, let's assume that Q2 is the highest for now.
Okay, all right.
So whatever is the highest, you put it there. I mean, yeah, earlier I had written Q3 and Q4. Of course, so for now, let's assume that there are only three Qs. And so we put it at the highest level and it will keep going down and it will finally run at the bottommost level, okay, when it has used all its time slices. Okay, so this was too simple an example. So example two, let's make things a bit more complicated and let's say two jobs. One short and one long. Okay. So in this case, we'll see how MLF Cube tries to somehow approximate the behavior of SJF or STCF. So SJF and STCF, if you remember, like shortest job first, shortest to completion first. Okay. And okay, so
Sir,
yeah.
sir, in the previous example, have you applied rule 4B when the process goes to Q0?
No, I have not applied. But Q0 is the bottommost level. So, and anyway, the job does not release the CPU before its time slice because it's a long running job. So it stays at that level because that's the bottommost level.
So rule 4A will not be applicable at the bottommost level.
Yeah, of course.
Okay.
You can't like reduce the priority anymore. Okay, so let's see now there are two jobs. So A was there. So A, the same as previous example. Okay, so it runs for 200 millisecond as it did. So this was T is equal to 200. And but now another job B comes at T is equal to 100, let's say, and runs for just 20 milliseconds. And the time slice we are assuming to be 10 milliseconds. Okay. Good. So what will happen in this case? So again, let's take Q2, Q1, Q0. Zero. So the first job A comes. So I'll try to use different colors for the jobs. So A uses the 10 seconds on the first level. Then till now B has not arrived. So it is going to be exactly as the first example. And then here it runs and goes till T is equal to 100. Okay. Now B comes. And B will be put in the topmost queue because of rule 1, I guess. No, because of rule 3. If a job enters the system, it is placed at the topmost queue. So B is put here. And which job will run? Will B run or will A run now?
B will.
B will. Because B has higher priority, it is in high priority queue. So B will run for here. B will come and B will run for its time slice, 10 milliseconds. But it also like finishes its time slice at the highest level. So it will be demoted. So now B will come at Q1, but still B will run because B still has higher priority than A. Okay. So B will come here and B will run. And now B has finished. So when B finishes, now there is no other job which has higher priority than A. Now A will get the CPU. And A will run after that. And maybe at T is equal to 220, it will finish. Okay. So is this example clear? Any questions about this? So yeah, basically, suppose a job comes. So what MLFQ does is treats it as a short job. Or assumes it's going to be a short job. So now, if it is short, and places at like highest level. So if the job is actually short, it will finish in its time slice. And if it's not short, then it will move down the queues in priority. So somehow then you see that shortest jobs will be finished first somehow so that is why we can say that MLFQ approximates the behavior of SJF. SJF. Okay. So any questions about this till now?
Sure.
Yeah.
So I had a question, not exactly related to this, but like if a job's completion time is more than the time slice, would it ever give up control before the time slice finishes?
I mean, depends. So if it does IO, then it can. So
So,
it will.
but then wouldn't it be removed from the ready state?
No, but it will give up control and then it gets back the IO. Then it will come back to the queue.
Okay, so it won't be inserted at the top of the queue then.
It will be inserted at the top of the queue.
Okay, so but like it will never remain at the same level, right? I mean,
Why not? It gave up the CPU. Okay, we'll come to these things, and still, if your question remains, we'll address that. Okay.
okay,
Next, we are going to do talk about IO. Okay. So we'll see such things actually. So let's take another example which is with some input output requests. Okay. So what does rule 4b says? That if a process gives up CPU, keep it at same level. So this is why is it done? So that the interactive jobs which use a lot of IO, they release the CPU before the time slice is complete. And so we don't want to penalize them. We want to reduce their priority. And keep them at the same level. And I mean, this serves our purpose because now their priority will not be lowered. So since they are interactive, they'll keep getting the CPU and the interactive processes will be fine. Okay. Okay. So for example, so in this example, in addition to A, there is another job B. which uses the CPU for 1 millisecond, let's say, and then releases it. Requests for IO, let's say. Okay, so what happens in that case? So again, we go through the same picture, Q2, Q1, Q0. And so t is equal to 0. So A runs here, and suppose B comes at t is equal to 100 again. So A comes here, it uses for 10 milliseconds, comes here for 10 milliseconds, then goes from here to here. Now it, like, this is t is equal to 100. Now B enters, but it uses the CPU only for 1 millisecond. Let's just get like this. And after that, it releases. So then again, A gets it. So A then runs for like 9 seconds, 9 milliseconds, let's say. Then B again comes. Now it has completed its IO. Now it gets here. Then again A gets it. And then so on. So why this is happening? Because B is remains at the high priority queue, and it will always run before A because it is in the high priority queue, and it will not be moved lower because it is releasing the CPU before its time slice is finishing. Okay. Is that okay? Is that clear?
So when these IO jobs released, get released from the CPU, will the scheduler wait for a time slice to complete, or is it scheduled immediately?
No, it will not wait for it to complete because that's waste of resources, right? So that's what is happening here, if you see. So the time slice, if suppose was 10 seconds, then this job used the CPU only for 1 second. And now for the remaining 9 seconds, so this for 1 second, and this is for 9 seconds, 9 milliseconds, it was given to A. Or sorry, it should be for 10 actually. It should not be just for 9 because A should be given its full time slice.
So in that case, will it be in sync with the timer interrupt?
No, so anyway, the time slice or even the smallest quantum after which the interrupts happen. So even 1 second has to be a multiple of the timer. 1 millisecond has to be a multiple of the timer. So
okay. That's
whatever
okay.
whatever the smallest quantum is after which an interrupt can happen, that has to be like the multiple of the. I mean, that is the timer interrupt. And then whatever the smallest time of process can be allowed by the scheduler has to be a multiple of that. So if this is 1 millisecond, then this 1 millisecond has to already be a multiple of the what do you call it? Timer interrupt.
Okay, sir, got it.
Okay.
Sir, but what I understood from his question was, does the job A have to run for 10 milliseconds now, or if the job B returns from like IO at suppose 5 milliseconds, will the
Okay.
job?
So if that is the question, then yes, then B will run first. Well, I mean, B will run if it returns from. Good question, actually. That will clarify some doubts. So if B comes back at 5 milliseconds, then B will get the. Okay, no, wait. I think in that case, B should get, and there should be an interrupt because now there are 2 jobs, and yeah, So whenever there are two jobs which are there and one has the higher priority, then the CPU will interrupt one job and run the other one. So it will be interrupted and B will take the priority. A will be interrupted. So if B comes back at 5 milliseconds, after 5 milliseconds, then B will run again. Because B has higher priority. There's no point in making B wait, a higher priority job wait. Even if the round robin slice of A for its particular queue is not finished, it will be interrupted. Okay?
Okay, sir.
And we'll see actually why this makes sense in a while also, that because the time slices also will vary for different levels. And that is why it asking a process to complete its time slice, it doesn't, it should not be the case. Okay. So, thanks for the question, Shweta. It was, I had not clarified that. Okay, good. So, all right. So this is the basic mechanism. But let's think about some problems with this. Anyone?
So an interactive job which takes just somewhat longer than the time slice, that takes somewhat longer than a time slice and then wait for IO, that would just keep getting demoted and would end up in the last queue.
Yeah, and what is the problem with being in the last queue?
It has the least priority then, and it won't be
It has a
interactive.
least priority. There is one slightly bigger problem. I mean, you are on the right track, but there is not just least priority. So if just suppose that I'll give a moment more to for other people to think.
All jobs will keep dumped to the last queue and it will be waiting. Like there'll be many jobs least.
They keep waiting forever. So if there are jobs which are at the higher queue and they are using the CPU, then there is no way to run any of the jobs. So if they can saturate the CPU somehow, if there are jobs at the top level which can saturate the CPU, then the jobs at the bottom queues will not get any CPU at all, ever, with the current policy. Right?
Yes, sir.
So that is the problem of starvation. If there are too many interactive jobs, then they will use up all the CPU time and the CPU intensive jobs will not get any CPU. And they will starve. So this is what is known as starvation. Okay. Good. So this is one problem with this approach. Another problem is, can you think of a way that even though you are not very interactive job, how can you still remain at high priority with the current set of rules if you want to game the system, let's say?
You can just run your own timer and release the CPU before the time slice finishes.
Exactly. So second problem is gaming the scheduler. So what is gaming? Doing something sneaky. to get more than your fair share. Okay, and how can we game the system? By releasing the CPU before the time slice is complete. So what will the scheduler do? We'll keep it at the same level. And we'll keep assigning it CPU again. And so like if you use like something like 99% of the time slice, then like basically you are using most of the CPU time. Okay. So this is another problem with the current scheduling policy. And the final problem is, what if a process changes its behavior? So suppose the process uses a lot of CPU initially, it is doing some computation and like it is using, so now it went down, but now it wants to be interactive. There's no way to do that, right? So suppose a process does a lot of CPU bound jobs and then becomes interactive. So it will remain at low priority, right? So these are the like three problems with the current approach. Okay. So can someone think of a solution that, okay, how to solve at least like some of these problems? Or how will we deal with this?
So for the third problem, couldn't a naive solution be whenever a job asks for IO, it can be inserted at the top queue?
Whether whenever a job asks for IO, it can be inserted. But the problem is it's not getting CPU time itself. So it will not even, it wants to ask for IO, but it's not getting CPU time because it's low priority.
Yes, sir.
So what we can do, like just like, so the attempt is going the thing that is going to be done is increase the priority of all the jobs periodically. Okay. So this is like, so let's try another attempt at, so this was the first attempt that we tried. Now another attempt is, it's called priority boost. Okay. So the idea is to boost priority of all jobs periodically. So which problems does this solve of the three? So, okay, let's write it as a rule first. So this is going to be rule 5. After some time period S move all the jobs to the topmost queue. Okay, so which problems does it solve of the three? So first was starvation, second was gaming the scheduler, third was change in behavior of the process.
I mean, doesn't it solve all of them?
No, it doesn't. It doesn't solve the gaming the system part. So the job still remains at the top level. It keeps releasing, and the other jobs which are CPU bound again will go down, and so on. They will. I mean, so the still some like clever programmer will be able to get a lot of CPU time by remaining in the top queues because this is only done being done periodically. So yes, but it does solve the first and the third. Okay. So how does it solve starvation? Of course, processes are guaranteed not to starve. Because they will get CPU time in round robin after getting to the topmost queue. Is that clear that this solves the starvation problem? Any question about this? And it also solves change in behavior problem. How? If there is a CPU intensive process that now wants to become interactive, then it will be moved to the topmost level and now it can remain there if it has become interactive. So if a CPU bound job becomes interactive, it can move to the top level and stay there. Okay. So there's an example in the book. I'll like briefly outline that. So what happens is suppose like Q2, Q1, Q0. So without this rule and with this rule, so suppose again there was A which was doing this, and then came like two interactive jobs which were using the CPU in tandem. Okay, and then this guy is just not getting any CPU. This just goes on. So never get CPU again. But now periodically, suppose this guy moves up. So what is going to happen in that case? So let's say like whatever, every 50 milliseconds this happens. So suppose this first is equal to 100 here. And after that it never gets. So here, here, here. Then these guys come and then they run for like 50 milliseconds together. Should have been green. Get what it was. And so let's say they are running each for 10 milliseconds and now it becomes 50. And then with this guy, then again this guy maybe he's before this job in the queue and now this job will get for 30 milliseconds. Or sorry, whatever the time slice is, that is 20 milliseconds, right? Or 10 milliseconds. Sorry, mistake. It should be 10 milliseconds. And then, so it runs here, the blue job with these jobs. And now it has used its 10 milliseconds. So it goes down. I mean, not, it goes down, meaning again, it just doesn't get. But then these jobs run again for like 50 milliseconds. And then this guy will again insert it in the topmost queue. And then he'll get some CPU time again. Right? Is that clear? So the book has a better figure, of course, because they have like made it not by hand. So you can have a look at that. But this is exactly the example that in this case, this does not star, and now if it becomes interactive also, then it will remain at the top queue. If it starts releasing the CPU, then it will not move down. So any questions about this? No? Okay. So this is like without priority boost. And this is with priority boost. So here I'm not showing that. So after using its time slice, it would be demoted to this level, but I'm not showing because it does not get any CPU time there. So like it would be sitting just here. And then when the 50-second time, so that S was 50 milliseconds. So after that time is up, it will be sent again to the topmost level, and then it will be given the CPU in round robin fashion. Now, if it again uses its time slice completely, then it will be demoted. And if it does not use, then it will remain at that level. Any question about that? Okay. Cool. So now the question is, what should S be set to? So how long this like periodic thing should be? And the bad part about this is there is no clear answer about that. It depends on, so again, so but at least one thing you can see that if it is too high, then the long running processes will start. And if it is too low, then okay, for long I wrote wrong. Then what will happen? Then the interactive processes will not get their fair share. Now this this job is now has gone up, and if there are many jobs like that, and if the time slice is too small, then this is not going to work, because now all these bigger jobs are basically more or less being treated in the round robin fashion, right? So the interactive jobs will not get their fair share. Okay, so that is why this S should be chosen carefully, but there is no like very clear answer of what this S should be, and it would be tweaked according to whatever the system requirements are. How, like, what is, how many short jobs are there typically, and so on. Okay, but still we haven't solved the gaming problem. Okay, so suppose all long jobs started doing this sneaky business of releasing the CPU right before the time slice was up, right? So to solve that, what can we do?
We can change the length of the time slice. Like,
But then the process will accommodate that, and then they'll release the time slice before that.
I mean, make it random.
Make it random, okay. Yeah, but then if in the random thing something very long comes, or if the time slice becomes very long, then that is also not very useful. Randomness has its own problems, right? And when you're scheduling something, you don't want to like assign random time slices. There can be like a slightly simpler and better approach. So this is going to be for gaming the scheduler problem. Okay. So which rules were problematic for this? If we go back and see. So priority of a job is more or equal or less. That is still fine. The problematic thing is that, okay, we are saying that, okay, a job remains at the same level, then but if it releases the CPU, we should tweak this. This is not very correct because I mean this can be easily gamed, right? So like 4A or 4B, whatever it was, 4A and 4B are problematic rules. In fact, whichever said that we should keep the job at the same level, that is more problematic. Okay. So what should we do? We should do better accounting. Rather than just looking at when a job releases the CPU, we should see how much time it has taken altogether, or I mean, at that level, right? So we should not forget how much time a job has taken before releasing the CPU and count it in the next time. Okay. So what is going to be actually the rule? So the rule is going to be, so instead of 4A and 4B, now we have this rule 4, which says once a job uses all its time allotted at a given level, irrespective of in how many times. It will be moved down or it will be lowered in priority. Which is moved down 1 queue. Okay, so this is going to be our new rule. So is this rule clear? Okay, so let's see this with an example. Okay. So suppose again A was the same. And now some B came which was trying to game the system. By releasing the CPU right before the time slice or 1 millisecond time slice finishes. So what happens in that case if we don't have this rule? So Q2, Q1, Q0. So A starts here, comes down, A runs, then comes B, and B uses, and then just for like one time slice, now A runs, and then again B comes back and says, okay, I need something, and it is higher priority because it had released the CPU. It runs again, then A will just get it for one more second that the B leaves, and then B will keep doing this. So, Shaurya, does this answer your previous question now?
Yes, sir. So, but why does A get it for just one more millisecond?
Sorry?
Like, B is running for 9 milliseconds, right?
Yeah,
And A gets it for 1 millisecond.
yeah.
So, like, does there some need to be 10? Like,
No, so that's what I'm saying. Now B comes back. So now B is higher priority, so A cannot run, going by rule 1.
yes, so like, but why does the sum need to be 10?
Why does it need to be, why it doesn't need to be 10? So you're saying that why doesn't A run for 10 milliseconds?
Like, could A run for 3 milliseconds, suppose?
I mean, because B came back after 1 millisecond. B is greedy.
Oh, yeah. Like, coincidentally, their sum is the time slice. Like, that's.
Ah, okay. Yeah, it might not have been the time slice. Yes. Actually, yeah. So, I mean, B could have been just released it like 1 second before. So it might have been 8 and 1 and then again 8 and so on.
Yes, now it's clear. Thank you.
Okay, good. Okay, so but what happens now with this rule? So with this rule, what will happen? A will be here, and then what will happen is that B will get first whatever 8 seconds it did, then A will get 1 second. Now B will get another 2 seconds, and now it has finished its 10 seconds quota. So now it will be moved down, but still it is higher priority than A, so it will run. Okay. So again, suppose it runs for 6 seconds because suppose it releases the CPU after every 8 seconds. Now for 6 seconds it ran, and suppose this was just 1 second, and then it again released the CPU for 1 second. So for 1 second, A gets it. Then again it uses it for 4 seconds. Now it has finished its quota of being here on this level. So again, A will run now for 10 seconds and B will run again for whatever 8 seconds or 4 seconds, however it's like designed. Because now it is not in control of when to leave the CPU and so on. Now the round robin will decide because now it's at the same level. If it wants to release after 8 seconds, that's up to B. So suppose it releases after 8 seconds, then A will run for 10 seconds. 8, 10 will go. Okay. So this is B. Is this clear that what this process does of what this new rule 4 does? This new rule 4 says that, okay, doesn't matter how many times you have released the CPU, I'll bring you down after you have finished your quota at this level.
Is that quota the same as the time slice, or like it can be different also?
So now it can be different. Now so earlier it was the time slice was that, okay, if you finish one time slice, but now this quota can be different than the time slice. Now they don't have to be the same. When after this new rule 4, they don't have to be the same. Because earlier the thing was tied to the demotion rule, or staying at the same level rule was tied to the time slice. That, okay, if you finish your time slice, then you go down. If you don't finish your time slice, then you remain at the same level. But now you can, so now there are these two parameters you can say. One is the time slice, and one is the allotment of the you know uh, how much allotment at each level the time is allotted, for. So maybe you don't want just after one time slice for a process to go down. Maybe you would want it to run maybe 2 times, 3 times before the, like you know uh, for 2 or 3 time slices before you demote it, because otherwise the cascading down will be too quick. So you might want to slow it down by making the allotted time a multiple of the time slice. I mean, yeah.
Sir,
Yeah.
sir, if we make the time slice equal to the quota, then basically the CPU is overlooking the importance of interactive processes, right?
No, it's not overlooking the process, because if a process is interactive, then anyway it will not use its time slice or the quota. It will keep releasing, and it will stay at the same level for a long time. And
But
then what will happen? Then
now
what?
the rule is bringing down its priority.
Yes, it will bring down its priority, but the so generally, so that's how these parameters will have to be set, that it will bring down its priority, but by the time it reaches some lower priority level, again the S will kick in, and it will bring it to the top priority level.
Okay, okay.
So these all the rules move in tandem, and it's not just that, okay, you keep bringing down, because not just one process is being moved down, right?
Okay, okay.
So if there are many interactive processes, only the ones which use all their CPU time will be moved down. If all of them are using, then they are all being moved down. And then, in that, only the high priority. And then, as I said, then finally they will be brought back. All the processes will be brought back to the topmost level. Okay?
So shouldn't B run for 4 more milliseconds when it gets demoted from Q1?
No, so that depends on the queues, whatever the policy is. So now you have a queue, and so whether you are doing first come first serve, and whenever you are adding new processes to the queue, are you adding to the front of the queue? Are you adding to the back of the queue? It depends on that.
Yes, sir.
Okay, so but the basics are like these 5 rules, and that is the main framework of a multi-level feedback queue. Okay, so now there are some questions, as one very important question is how to parameterize. So just now, I think Prithvish, you were asking, right, about this interactive process bringing down the priority question.
Yes, yes, sir.
Yeah. So again, so these are questions which become important. So let's say that how many queues should be there? What should be the value of S? what should be time slice or allotted time? What should be allotted time at each level? And as like, so these are the like main parameters, and like again, no one answer which fits all. Okay, but there is one thing that most of the MLFQ schedulers implement, and that is have longer time slices and longer allotted time for lower priority queues. So the point is that if like actually the scheduler goes down and now there are no high priority jobs to run, then it should give more priority to the, it should give more time because these are CPU intensive jobs. So it should give them more time. Okay. So for example, in the book, they mentioned Solaris, and on that, like it has, so queues, it has 60, and time slices are 40 millisecond at the highest level, or 20 milliseconds highest level, and hundreds of milliseconds at lower levels. And if you see in the book, there is a diagram which like shows that, okay, how does it work when you when like longer and longer time slices are given as you come down. And that is helpful because these are actually CPU bound processes, so they should be given more time of the CPU. Some other schedulers use some mathematical formula to like determine some like priorities, or sorry, not priorities, the time slices, etc., and S. And there is another thing that some OSs reserve the topmost priority for OS work only. So any user process will be lower priority. Okay. And then there is some like, user can also give some advice about which processes to run which process to like move up the priority or down the priority slightly. And this is done by the nice function. And you can see the man page of this to learn more about this. So this you can consider the ungraded homework. And so now these are the 5 rules. First was that if priority of A is greater than priority of B, then A runs. If 2 priorities are equal, they run in round robin. When a job enters the system, it enters at the top. When a job uses its allotted time, then it moves down, does not matter how many times it has used the CPU. And after some time, all the jobs will be moved up. So these are the 5 rules which constitute a multi-level feedback queue. And as we saw, no a priori knowledge is needed about how long a job is going to run. And the overall performance approximates SJF or STCF for short jobs, and it is used in some form across like extensive matrices. So okay, my writing goes bad when I try to write fast, and since time is over, I was. So Windows NT had this, even like Unix had this, and yeah, a lot of modern OSs, which also which they also use some sort of multi-level feedback. Okay, so yeah, I've gone slightly over time. It's 10:52, but I can quickly take some questions if there are any. No questions? Okay, good. So by today, end of day, or should be by evening, you should be getting your first assignment, and it will be due by the next class. Let's say Monday should, I think, and I mean not next class. I mean 10 days after the Monday, not this Monday, of course. And yeah, so good luck. I'll upload it on the assignment. Okay. Any questions? Anything?
So what will be the assignment on?
It will be some basically the process API that we did to basically make a shell, design a shell, and then it should have certain functionalities, and it will be told in the assignment what kind of functionalities you should have. So I outlined how a shell works, and that's what you have to implement now in a C program.
Okay, sir. Thanks.
Okay. Thanks for joining, everyone. See you on Monday.